right, here's an optimization example. So the problem is a rectangular cake dish is designed by cutting out squares from corners of a 25 centimeter by 40 centimeter rectangular tin plate and then folding that metal to form a container. What size squares must we cut out to produce the cake dish that will have the maximum volume? So I'm going to label these sides. So this is 40 centimeters and this is 25 centimeters. And we want to cut out these X's to create this container over here. So step one is we're going to draw a large clear diagram. So here is that inside. And then we have the sides that are going to fold up. So this would be our base, the bottom of our container. And then these boxes are going to be cut out. And they are all equal in length. So we know that this distance here is 40 centimeters. So we're going to let this be X and X. So we're going to take away two X's. So this distance is going to be now 40 minus 2X and 40 minus 2X. Then the distance along here, before we fold it up, is 25 centimeters. Well, we're going to have to subtract out an X and an X again. So this distance here is 25 minus 2X. And that would be the distance here and there. So I'm going to highlight this expression and this expression. So when we fold it up, this side is 40 minus 2X. This width is 25 minus 2X. And that height of the container is X. All right, step two is we want to construct a formula with a variable to be optimized as a subject written in terms of a single variable X, and then figure out its restrictions. So the volume of a three-dimensional figure is length times width times height. Well, this up here in our figure is our length, this is our width, and this is our height. So we're going to let X equal the centimeter height that's cut out. And now we're going to write our equation. So the volume of X, so we're going to write it as a function, is the length expression, 40 minus 2X, the width expression, 25 minus 2X, and then the height, X. And then what we're going to do is we're going to FOIL this out. So we're going to start by FOILing the two binomials. And we're going to get first 1,000 minus outside 80X, inside minus 50X, and then last, positive 4X squared. Then what we have to do is we have to distribute that x into all four terms. So our equation for our function is 1000x minus 130x squared. How I did that is combine those two middle terms that are alike, and then plus 40x cubed. The unit of measure for volume is length times width times height, or centimeter times centimeter times centimeter, or centimeter cubed. That is the volume function. Now we need to come up with what would be the restrictions for that domain. What could we not let x be? So if we think about our flat piece of paper, we can't have x be a negative number, so it has to be greater than 0 or it would be flat. But then if we go too large on our x, it'll go flat again. So if we go up to this box here, what would be that highest x value? So we want this width to not flatten out. So we're going to say x has to be not flattened back out. So we're going to take 25 minus 2x, which is that width. We want to make sure it's also greater than 0. So we're going to solve this for x. So we're going to subtract 25 from both sides. And then we're going to divide both sides by -2. When we divide by a negative number in inequality, we have to switch the inequality direction. So 12.5. So our x value has to be somewhere greater than 0, but less than 12.5. Let's go back up. If we cut this piece of paper or tin in half, we'd have 12.5 here and 12.5 there. If we cut 12.5 off each side, it would go back to straight up flat. So that is our domain restriction. You could also graph this function on a coordinate plane. And you would see that this is going to be a parabola, a cubic function. And you'll have something that might look like this. Here is 0, and then here would be 12.5. This is the domain restriction right there between 0 and 12.5 if you were to graph that cubic function. All right, step 3. We want to find the first derivative using our power rule and then find those x values for which it is equal to 0, the critical points. So our function, I'm just going to write it down again for you, is in standard form 4x cubed minus 130x squared plus 1000x centimeters cubed. Now we're going to do the derivative. So we're going to bring down that 3 and then subtract the power. We're going to bring down the 2 and subtract the power. We're going to drop that x. Now we'll simplify it. So we're getting the derivative function to be 12x squared minus 260x plus 1000. There's our derivative function. Now we want to find out when would we get those x values to be 0. So we would let x equals 0 for dv dx. And we would solve this for x. We could factor quadratic formula, or use the graphing calculator to find those zeros. And that's what we're going to do. So let's assume that we went and used our graphing calculator and we found those zeros. Well, those zeros are x equals 5 or 16 and 2/3. Those are our two critical points. Step 4 says, if there is a restricted domain, such as the max or minimum may occur either when the derivative is 0 or at the endpoint, you want to show using a diagram for the sign diagram or graphical test. So remember, our domain restriction was somewhere greater than 0 but less than 12.5. Well, 16 and 2/3 is larger than our domain restriction. So we're going to eliminate 16 and 2/3, and we're going to focus on the critical point when x equals 5. So let's create our sign diagram. So here's 5, and we would want to test something to the right, and we would get a negative, and something to the left, and we would get a positive. And then we'd have 12.5 was our maximum, and then 0 is our minimum. So we couldn't go higher than this, and we couldn't go lower than that. So let me show you how you find that positive or negative. So you're now going to use your derivative function, dv dx, 12x squared minus 260x plus 1,000, and you would let x be, let's say, 1, and you would substitute 1 in for x. And what you get when we type that in is 752, which is a positive number. So that means everything a little greater than 0 but less than 5 is going to output a positive number. Now let's check something to the right of 5. Let's say 6. So we would substitute into the derivative function 6. I'm looking for that slope. Is that slope positive or negative? Is it increasing or is it decreasing? So I'll type that into my calculator. And what we get for a value is a negative value, a negative slope. So that's anything greater than 5 but less than 12.5 is going to be a negative. So we're seeing a sign change going from a positive to a negative. So this has to be the max value for x. So now we say identify the optimal solution. Also consider endpoints. So our maximum, there is a local max when x equals 5. There's a global minimum, but it's outside our domain. Now we need to go ahead and find that answer in a full sentence. So the max volume is obtained when we cut 5 centimeters off each side of that flat piece of tin plate.